In this video, we're going to learn about polar integrals. Integrals tell us the area that's under a curve, and polar integrals do exactly the same thing, but they do it in a slightly different way than rectangular integrals. Whereas rectangular integrals, you have a series of rectangles under your curve. Here we've got a series of sectors of a circle. So the big formula that we need to know is this one. This is how you find the area under a polar curve. The explanation for why that's the formula is on the next slide. So like I said, instead of having a series of rectangles under our curve, this is our curve right here, underneath it we have a series of pieces of a circle, which we call sectors. Right here, there's a sector, there's a sector. It's basically the same idea as the rectangles, that we have a lot of sectors, and then we add them all together, and that gives us the area under the curve. So the area of a sector, the easiest way to think about it maybe is with a proportion, where we have the area of a sector over the area of a circle equals the angle for the sector over the angle for the entire circle, which is 2 pi. And then we'll call the area of the sector A, just to make it a little bit easier. Area of a circle is pi r squared. So when we simplify this formula, what we're looking for is the area of a sector, so we get A equals theta over 2 r squared, where theta tells us like the central angle, this angle here, for our sector. So we have this formula. The thing that I've changed here, instead of having theta, this angle here, we don't know where this sector is going to be in a circle, so we can't just say maybe that this is theta, but we know that whatever this angle that this line is at and that angle that the other line is at, we could find the difference between the two, so really delta theta is a little bit more accurate for what we're doing. And then because we're working with an infinite number of these sectors, this delta theta is going to get infinitesimally small, so instead of having delta, we just write d theta. So this is the area for one of the sectors, and then if we want to have the area for all of the sectors, that's where our integral comes in that we had on the first page. So for an example, we can use an integral to find the area of the inner loop of the graph of r equals 2 plus 4 cosine theta. The first thing we need to do is figure out, well, what does the graph look like? So we can draw a graph of that. I used Desmos, but you can use any graphing app or your calculator, or do it by hand. So we have the inner loop that we're looking at, and I've kind of shaded this in here so that we can see that's the area we're looking for. And if you notice, the inner loop goes through the origin, like that's sort of where it cuts off. It goes around and then it comes back to the origin. So our radius is equal to 0 a couple times. So the first thing we need to do is figure out what our angles are that we're looking at. So what theta do I have to plug in to get the radius to equal 0, because that'll give me those 2 points where the loop opens and closes. So I just take r and set it equal to 0. So then rearranging that, we have cosine of theta equals -1/2, and that happens at 2 different places between 0 and 2 pi, which would be 2 pi over 3 and 4 pi over 3, which you should also be able to figure out from a unit circle. So our integral goes from the smallest angle to the biggest, which is going to be important later, so it has to be increasing. Smallest has to be on the bottom, biggest has to be on the top. And then 1/2 times r squared d theta, and then I evaluated this with the calculator to get 2.174, so that's that area of the inner loop right there. Here's one for you to try that's similar. So we have to find the area enclosed by one loop of the 4-leafed rows r equals cosine of 2 theta, and I would suggest by drawing a graph first. So pause the video now, take a couple of minutes to try the problem, and then when you're ready, restart the video and we'll look at the solution together. Alright, so first I drew my graph over here, and all 4 of these leaves, this leaf, and this leaf, and this leaf, and this leaf, they're all the same size, so it doesn't matter which one we find the area of. I know that my formula is r equals cosine of 2 theta, and again, each loop goes through the origin, so I'm going to take that and set it equal to 0, and figure out what angles this happens at. So inverse cosine of 0 gives me pi over 2, 3 pi over 2, 5 pi over 2, etc., etc. And then that's what 2 theta is equal to, because I had cosine of 2 theta. So 2 theta equals all of those. And I just divide each angle by 2, so pi over 2 becomes pi over 4, 3 pi over 2 becomes 3 pi over 4, and so on and so on. And like I said, it doesn't matter which leaf you're looking at, so I just took the first two, and if you want to graph it on your calculator, you can change the window settings so that your min theta is pi over 4 and your maximum theta is 3 pi over 4, and that'll show you that you get this leaf. If you go 3 pi over 4 to 5 pi over 4, you get this one. 5 pi over 4 to 7 pi over 4 gives you that one. And then this one is kind of interesting because that would be 7 pi to 9 pi over 4, or it would also be negative pi over 4 to positive pi over 4. But like I said, it doesn't matter, so we're just going to pick two of the values, and I just went with pi over 4 and 3 pi over 4 for my integral, which is the shaded leaf. So we do 1/2, and then from our lower end to our upper end of r squared d theta. Evaluating that with calculator, I get 0.393. The other thing that we might have to do with polar coordinates is find the area between two curves. This looks pretty similar to the washer method of finding volumes. So our 1/2 is still here because basically we have 1/2 r squared d theta. The thing that changes is that our r squareds, now we've got two of them because we have the outer one squared minus the inner one squared. And notice this 1/2 is multiplied times the entire thing. So if you want to write two integrals, it'd be 1/2 times the integral of the outer squared minus 1/2 times the integral of the inner squared. So just make sure that 1/2 gets distributed to both of them. Here's an example. We are finding the area that is outside r equals 3 and inside r equals 2 plus 2 cosine theta. So first I need to graph. This is r equals 3. It's just a circle. And the other one, 2 plus 2 cosine theta, is the blue graph right here. So if I'm going outside of the circle and inside of the other one, it's this shaded area. First thing I need to do is find out where these two curves intersect, because I need to know I'm taking my integral from this point to this point. So I set the two equal to each other, 3 equals 2 plus 2 cosine theta, and then I'm going to solve that. So if I rearrange it, subtract 2 from both sides, I get 1 equals 2 cosine theta, and then divide by 2 to get 1/2 equals cosine of theta. Using my unit circle knowledge, I know that theta has to equal pi over 3 or 5 pi over 3. But if I go from pi over 3 to 5 pi over 3, I'm going this way around the circle, because here's pi over 3, and then I go all the way around to 5 pi over 3, which is exactly not the area that I want, because that's not even shaded on that side. So I need to go this direction, but my integral will always take me from the lowest to the highest around, counterclockwise around the circle. So I need another way to represent 5 pi over 3 that will make me go this way. And I know that the coterminal angle with 5 pi over 3 is negative pi over 3 because I'm going negative pi over 3 in this direction. And that is really good because now, if I write my integral from negative pi over 3 to positive pi over 3, I start here at negative pi over 3 and I go around this way to positive pi over 3. So that's the direction I want to go in. And basically, just to reiterate what I said earlier, this lower limit on the integral always has to be smaller than the upper limit if you want to have a positive area. Alright, so once I figured out that that's where I'm going, negative pi over 3 to positive pi over 3, now I just fill in the rest. So here's my 1/2, and then my outer graph, squared, is the blue one, the cosine one, and minus my inner, so the green one, minus that one, squared, d theta, and evaluating that with calculator, I get 4.653. So here's a really similar example for you to try. We have the same graphs, r equals 2 plus 2 cosine theta, and r equals 3, but this time we're going the other way, meaning we have to find the area that's inside 2 plus 2 cosine theta and outside r equals 3. So pause the video here, work on this problem, and when you're ready, restart it and we'll look at the solution for it. Alright, if you want, you can find the intersections again, but they are the same as last time, pi over 3 and 5 pi over 3. This time, we want this area that's shaded in, so we're going from pi over 3 around to 5 pi over 3 is not a problem because that gives me the right side, that gives me the correct side of the circle, the part that's shaded in. So that's what I need. Pi over 3 to 5 pi over 3 for my integral. 1/2 the outer function squared, so 3 squared, minus the inner function squared, which is this one, which is 2 plus 2 cosine theta squared. And then d theta, evaluating that with calculator, we get 14.077. And that is it for polar integrals. If you have any questions, write them down, email me, ask me in class, and I'll see you in the next video.